Last time we proved this theorem about homogenization, that so this theorem, that given a circuit of size s, doesn't matter what the degree is, degree can also be exponentially large, but if you, as long as you are interested in lower degree parts, they can be extracted by using an efficient circuit. Okay, so the size is merely quadratic, it's this SD square. Any questions? So the next structure result that we will show is to do with computation of derivatives. Okay, so we'll use dou xi to denote the first order derivative of a polynomial with respect to the variable xi. This is a linear operator, and the most interesting thing is that it satisfies Leibniz rule, okay, which is it's basically the action on the product. So the action on product is differentiating one at a time and taking the sum. So the effect of this is essentially to linearize a problem. So this actually linearizes problems. The reason why differentiation is so helpful generally in mathematics is because of this identity. So it can make non-linear problems somewhat linear, okay, and then you can use linear algebra algorithms to solve ultimately. And the obvious thing that if f is constant with respect to xi, okay, so these are the properties, or you can also take them as the definition. These are the axioms defining differentiation. Fine. So how do you compute this at the level of circuits? So we will prove this theorem by Bauer and Strassen. From 83. So let's see in many variables be a size s, degree d circuit. Then there exists a circuit D whose size is roughly the same, size is order s, and depth is also roughly the same. Yes, I wanted the depth, not degree. So depth is also the same, order d, that simultaneously computes all the derivatives, first order. Dou xi c. Okay, so in the same size and depth, you can actually compute all the derivatives, all the n derivatives. This is the theorem by Bauer and Strassen. So actually in the beginning it wasn't even clear whether you can compute the derivatives efficiently, and this theorem is actually giving you much more. So how do you prove this? Right. So most of these proofs in circuits are based on induction, on size or depth. So in this case we will do it do basically induction on the size, but also on the depth. So we'll basically I mean, if you are looking at a variable, then differentiation is very easy, right? So derivative at that variable is 1, and otherwise it is just 0. And in the leaves you have actually variables. So you start from the leaves, your inductive argument, and then gradually go to upper levels.
What is its definition of del xi? This is property that you can split.
What is the definition of differentiation? The definition of differentiation is given here. This is how it is defined. It's an inductive definition.
It's an operator basically. It's a linear operator which also called
Yeah, including the linear operator thing. So these three things give you the definition of differentiation of any order.
If f is xi, what is del xi f?
Oh, so then yeah, that maybe that
But it should be 1. I guess.
it should be 1, yes, and that you are not getting by xi times 1.
Yeah, I mean that will be 2. If f is xi, so base case is not different 1.
Yeah, so we can add the base case. So that defines differentiation, and this is how. So you can basically implement this definition from the deepest levels of the circuit and then move upwards. Yeah, so the idea is very simple and the implementation is also not hard. So let's do that. So it will be a constructive proof. You will actually get an algorithm to construct D, efficient algorithm. So we prove existence of D by induction. On the size S. So if C is a variable, then obviously we are done by the definition of differentiation. Else,
So here, will the blow up in size not depend on the number of variables? Because suppose C was a variable, then the circuit that computes all the derivatives, there should be like n many. Should not have like n many.
So first of all, usually the way we have defined it, size includes n. And secondly, yeah, that has, I mean, n has to be included in S, otherwise we should just simply look at the roots, the outputs, they are n.
So when we say
So order S means that, well, n is subsumed.
so Sn is order S.
Sorry?
So suppose the circuit has size S,
Mm-hmm.
and then we constructed a new circuit of size say S times n.
No.
No.
Something like additively it will happen, and as S is much bigger in some sense than n, then that won't matter.
Oh, okay.
No, so what the expressions written here are correct.
Yeah, no.
So I am just reminding the definition. The definition is size includes n. It's not S times n. Okay, so otherwise when when circuit is not just a variable, so then it has things above the leaves, and you pick the deepest gate, call it V. So let V be the deepest gate. In C, and denote V's children by U and W. Maybe I am assuming that the fan-in is 2. That is possible. So let me add that assumption. Fan-in is 2. So you have V here. So the circuit is above V, and V is the deepest, one of the deepest gates, which means that U and W are not gates, so they are just variables or constants. So what do you do now for induction? So obviously the idea should be to just surgically remove these three nodes, right? So remove them from the circuit, replace them by a new variable y. Think of it as a new variable and a new leaf. So that is the modified circuit, that it has clearly smaller size because three things have been removed, replaced by one. So the size has fallen, and so for the remaining circuit, you know that by induction hypothesis, all the derivatives can be computed, including this new variable y, right? So and together with that, use Leibniz rule, use the axioms of derivatives to finish the proof. So let's do that. So consider circuit C V equal to y. So y is now a new variable where subtree of V is replaced by a new variable y. Okay, so we have defined this. That's a smaller circuit. So the size of this circuit is smaller than S, clearly. So what this means is that by induction hypothesis, there exists a circuit D prime of size. So this modified circuit has size at most S minus 1. So let's say alpha times S minus 1, where alpha is a constant that we will fix later. Okay. So induction hypothesis gives you alpha times the size, which is at most S minus 1. Size circuit D prime, computing all the derivatives. So dou x1 C V equal to y dot dot xn C V equal to y, and finally the new variable. Okay, so these we have a circuit computing all these n plus 1 things simultaneously. So now we have essentially three kinds of circuits and corresponding polynomials. So original was f. F at V is the polynomial computed at V inside f. So that's a very small polynomial, and f V equal to y is what remains after you remove the subtree and replace it by y. So these are the three relevant polynomials. These are the output of C V and C V equal to y respectively. So let us define these three polynomials. So let x prime be the variables appearing in the circuits U and W. Right, so these were the children. So either they are constants or they are variables. So x prime is at most 2. There are at most 2 variables. And what can you say about the relationship between these 3 polynomials? So in f v equal to y, if you substitute y equal to fv, what do you get? You get the original polynomial, right? So this is the basic identity. So this inner thing is this polynomial is in y, and if you remove y by substituting fv, you will get the original polynomial. So on this, let us do differentiation. So let us first write f as a polynomial in y. So this is basically x in f v equal to y. This polynomial has x's and y. In y, you are substituting fv. So that's the association. Yeah, so this is just to define the AIs. That's the definition of AIs. It just follows from the above observation. Okay, so this is the equation which we now want to differentiate, right? So let's do that. So differentiating it with respect to xj will give you, so ai y to the I is a product, so applying the product rule, you get this, and yeah, we are always thinking of this as y is always equal to fv, right, in this equation. So what is this? So let us look at the individual sums. So the first one, this one, which sigma gives you
Partial of fp equal to y evaluated at y equal to fp.
right. So partial of fv equal to y with y equal to fv, and the second one gives you with the sum.
Evaluated at the partial of y with respect to xj.
I want to write it like this. So you just differentiate with respect to y. Okay, no, so maybe we should do it in steps first. Yeah, so this thing, this other one, instead of, so to differentiate with respect to xj, you can first differentiate with respect to y, and then y with respect to xj. So use the chain rule that follows from the definition of derivation. So maybe I write that down. So this is equal to the chain rule, right? So first with respect to y, then with respect to xj. So on this you take the sum. So then this part is independent of I, so that comes out, and what remains with the sum is this. This remains, this is the sum value. With y always fv and xj y which is fv. Okay, that's it. So you differentiated in different ways. You differentiate this new polynomial f v equal to y, you differentiated once with respect to xj and another time with respect to y, and then you just did some simple operations. Now f v is such a trivial polynomial that computing dou xj is just some constant size being added, and both these derivatives dou xj and dou y, I mean both the derivatives of f v equal to y, they have already been computed simultaneously, right? That is what d prime did. So d prime already gave you these two values, and you just have to do some trivial computation to get the circuit for dou xj f. So the size of this is,
So if xj is not in fp, then dou of
right, yeah, so that is already contained. Yeah, so this I want to deduce from this that size of dou xjf is upper bounded by size of d prime plus some constant gates to do this multiplication and addition. And as we vary over j, what happens? Yeah, so as you, sorry,
Why are we using it?
yeah, x dash has to be used actually, otherwise this would seem like as you vary over j, you multiply by n. Yeah, so
I think it's because you can take d prime, you can first substitute for y v, and then that will increase the size by a constant, and then in two of the output gates you just have to modify it to add the
right.
whatever.
So otherwise you don't even add. The addition is not there actually. So that's an additional observation. Let's write it down.
Like computing two of the derivatives, you just have to multiply them with.
Right. So if xj is not in x prime, then the above formula gives you. So xj not in x prime is basically you are saying that xj is not in u, not in w. So then it is not in fv. So this part actually vanishes, this part. So this is just a transfer. So xjf is just xjf v equal to y at y equal to fv. Right. So whatever was computed by d, that is just being transferred. That does not take any size. So the size contribution, I mean the addition and multiplication will happen only when xj is in x prime, which happens only 2 times. So actually you get something stronger. So size of the final circuit D computing all the derivatives is upper bounded by well, D prime size is, okay, let's do it in 2 steps. So first you compute D prime and then you add some constant which will be alpha. Okay, so for the 2 variables xj in x prime, you will add multiply also. So these will be constantly many gates being added. So let's call that alpha. That's the constant growth. And let us use the same alpha for in the induction hypothesis. Is the alpha that was yet to be fixed is this alpha. So this is less than equal to alpha s minus 1 plus alpha, which is alpha times s. Okay, that's order s. Is that clear? And similarly, depth of D gets bounded. So that finishes the constructive proof to compute derivatives simultaneously without changing size and depth. Okay, so yeah, it's an interesting proof, although it is only using the definition of differentiation. But it is also inventing something about circuits, which is that you can remove a sub-circuit and replace it by a new variable. So that's an auxiliary circuit, and you are working with that auxiliary circuit to compute the original polynomial, right? So that is the idea which we will now mine in the next theorems. So we will develop this idea more generally, that when you look at the parts, various parts of a circuit, they are also computing some useful things. In a way, in this proof, they are computing derivatives already. So if you look at the parts of a circuit, you can actually see derivatives. You just have to combine them in a simple way. So let me write that down. So this theorem suggests parts of a circuit almost compute derivatives. Okay. So just have to look at the correct parts of a circuit and you will be able to see by combining in a simple way derivatives. So we will develop this theme to get a very strong depth reduction property. Okay, this is a property which was never seen in other models. Okay, so this property will say that if you want to compute a polynomial of degree delta or d, then there is no need to go beyond depth log d. So somebody gives you a circuit computing a degree d polynomial with depth arbitrary, say the depth is equal to the size. So then we will give an algorithm that will modify the circuit to another circuit of similar size where the depth has come down to log d. Okay, and that is a very surprising thing. It actually seems impossible that if originally the depth was d, how can you reduce it exponentially to log d? So we will be able to do it because of these hints which were available in this proof, that actually parts of the circuit are already computing useful things, and since in the end you are going to compute only a degree d polynomial, if somehow you are able to make sure that every multiplication gate doubles the degree, then the number of multiplication gates cannot be more than, I mean, in a path, the number of multiplication gates cannot be more than log d. Okay, so that is how we will get to depth reduction theorem. But before that, there is an open question for derivatives. Okay, so what does this give you if you want to compute derivatives of the second order? How much size?
They can be written as derivative of first order.
Correct. No, 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 not same size. You get a multiplication. Yeah, there is a multiplicative growth. Uh, because just to look at xi and xj, right? How many ij's are there? N square. So when you have this circuit D that has computed all the first order derivatives,
So in first order we are getting constant number of xj's for there was 4 lakh.
yeah. So the circuit D which is giving you all these dou xj's, naively what you have to do is,
Supply.
yeah, for every dou xj, again apply the same thing for a different or for another xi.
So first order. Then in third order size of the second order.
Right.
And that will multiply. I think as raised to
Right. So there will be a multiplicative growth.
instead of alpha, I think there will be alpha times n or something like that.
Right. Right. So you get order ns. Right. It's a multiplicative growth. So and then hence, I mean, similarly you can go to any order derivative. So maybe I write that down. That is kind of important, but a simple observation. So t order derivatives in, let's say, s times n to the t minus 1 size. This seems fair, right? For t equal to 1 you are getting s times n, and then similarly. Okay, so the open question is to improve this. So let's leave this as an exercise. And the open question is, could all the second order derivatives,
Will there also not be an alpha to the t type term?
alpha times t?
Yeah, but I don't think it will matter.
This is just like n choose t. This is n choose t. So can you compute second order derivatives, all of them, in linear size? So without paying much of a price, can you also go to second order from first order? Right, first order was a surprise, and maybe the surprise continues to second order. Right, there is no reason to disbelieve this, and you will not believe that if you do this, you will solve a very old practical problem. So this esoteric question, if you solve it positively, then you have solved a very, very practical basic problem of with a history of decades. Do you know which problem? Yeah, you will solve matrix multiplication in quadratic time. Yeah, you will solve it in quadratic. So currently n by n matrix requires n to the 2.41 or 38, yeah, 2.37 dot dot, and you will solve it in n square.
PIT sector will also be solved.
Sorry?
PIT will also be solved.
Well, PIT is practically solved. Nobody doubts.
I mean, after this,
Mm-hmm.
PIT will also be solved because
Yeah, no, but
we are
practic.
seeing all the cone by taking all the partial derivatives up to degree d.
No, second order derivative.
No, it does not.
PIT is
I
practically
mean-
solved already.
If second order is done, then third will be.
Why? There is no promise. Yeah, I'm not sure that second order implies third order. Just like first order didn't imply second order. This is related to fast matrix multiplication.
And so the complexity of various other problems.
Yeah, anything that depends on matrix multiplication. Basically, any linear algebraic computation depends on this. Sorry?
Polynomial factoring mode rupee.
No, that is too complicated. Anything that any linear algebraic computation is matrix multiplication based.
Simple
That has some
example would be
algorithm.
Euler shortest path, because it completely depends on one matrix.
I mean,
Much
you.
more simpler example.
I think you the list is literally into millions. Problems that reduce to linear algebra. In fact, I heard from insiders that all Netflix does to decide where to invest the money, what series to make, is matrix multiplication. So they just buy billions of GPUs and run matrix multiplication to solve this. I mean, essentially, it's a joke on ML. So ML algorithms, they ultimately do matrix multiplication. So if there is really a practical way to hasten matrix multiplication, then it helps them. Okay. Why this connection may not be obvious, so let us just go through this. So we will look at a polynomial that is related to matrix multiplication, and then we will differentiate it using second order derivatives to get matrix product. So let me just give the construction, because once written down it's easy. So the polynomial is this: you have two matrices, say for simplicity these are n cross n square matrices, A, B. So you are interested in A times B. So to get a polynomial out of this, you just consider the corresponding multilinear form. So you multiply on the left side by a row vector y, and on the right side a column vector z. So say A is the matrix with x1s, so x1 ij, and B is the matrix with x2s. So these are formal matrices. So there are these lots of x1s and x2s and y's and z's. Okay, so x's are 2n square many, and y and z are n many. So this is 2n square plus 2n variate. So what is the size of this polynomial? I mean, what is the smallest circuit you can think of for C? So size of this circuit, circuit size of this polynomial is at most, yeah, so it seems n cube, but you are wrong, because the magic, the magic is that this breakup significantly simplifies life. So you first multiply by y on the left, right? So that will give you only n square, and similarly symmetrically on the right side with b, and then it's only a question of taking inner product. So the circuit is order n square. Yeah, so this polynomial construction actually is not n cube, but only the size is only n square. And what about its second order derivatives? So if you compute the second order derivative yi zj, right, so that is your product entry. So that is that's just ABIJ, ijth entry for all ij. So if you can compute all these second order derivatives simultaneously, in size C, that will be n square. Then we have an optimal way. Right, so right, this actually seems even better than matrix multiplication algorithm. This is actually a circuit of size merely quadratic. There are n square variables and the circuit size is also n square, order n square. Right, so this is actually too good to be true. But you can modify it slightly. You can maybe give it n to the 2.1 leeway or n to the 2.2 leeway and ask the same question, right? Or n to the 2.36, and that will still break the word record if you are into word records. Okay, any questions? Fine. So now we want to prove depth reduction results. We'll start with formulas before moving to circuits. That is also how it happened historically. And I don't think this will follow from circuit depth reduction. So let's first do this depth reduction for formulas.
Just have like better, I mean smaller size block or?
If you use circuits, no, so in circuit reduction then we have to carefully check whether fan out is being preserved to 1 or not. Yeah, so usually for formulas you have to repeat proofs, because just proofs that work for circuits don't directly work for formulas, because in circuits you can just compute something using it hundreds of times. That isn't allowed for in the case of formulas. So we start with a result or even an algorithm to reduce depth to log degree. Okay, this is the goal. So it's not clear why you would conjecture this, but it was conjectured and proven by Brent. Okay, so because you have to note that the degree is in formulas, degree is like size, and depth originally was size, and now you are bringing it down to log of size. So it's an unbelievable reduction in the depth. So let C be a sizes formula. Then, so we are starting with the assumption that it's a sizes formula, no talk about depth. So depth could be as high as S, but the conclusion says that there is an equivalent formula of size will be poly S depth will be order log s. It will have more properties. So fan in will be bounded, and obviously formula, so fan out is 1. Okay, so bounded fan in is important. This shows that there is no chance of cheating. It is really an optimal result, because fan in is 2 of multiplication gates especially, and still only in log s. So minimal depth of multiplication depth required to get to degree s is log s. If you are below that, then you cannot even compute degree s monomials. So log s really is the minimum, right? So this depth is really an optimal at this scale. It's an absolute optimum. Okay. So how is this shown? So this is shown by identifying what will be later called frontier gates. So these frontier gates are always multiplication gates at which the degree suddenly jumps. Okay, so say the degree at the root is d, so then frontier gates would be those multiplication gates somewhere in the middle of the circuit where the degree is jumping from d by 2 to d. Yeah, that is not quite correct actually. Or maybe I should say that it will be a gate where right, I should actually say that it's a frontier gate is a gate where the degree of the children is less than equal to d by 2, less than d by 2, but at this gate it goes beyond d by 2. So it's the place where this d by 2 is being crossed. So those are frontier gates. So these gates are somehow important, and we'll work with them. And then we'll also need to modify the circuit using the frontier gates. So it will be a constructive process. It will be an algorithm. The proof will be an algorithm. So we assume in the beginning that fan in is 2. Let's start with this. So from the root, let us walk down looking for frontiers. So walk down from the root by taking the child whose subtree is larger.
So is it an algorithm? So how do you know the degree of the thing? That requires.
It's a randomized algorithm. Yeah. So practically this can be done. Yes. Actually, for formulas we will not talk about the degree. So it's more about the size. Then we have to change the proof for circuits. So consider the first node. Anyways, for formulas, size and degree are kind of synonymous. They are analogous to each other. So we will talk about the size. So consider the first node V in this walk that you are doing, whose formula size is less than equal to 2s by 3. So this is the first one, where the formula size drops below this threshold 2s by 3. Okay, so this is, think of this as a frontier node. We'll call this CV. So this sub formula we are defining it C sub V. So this is, let's say, V, and the path that you are, or the walk that you are taking is this. So you are coming down from the root towards the leaves, and the first place where the sub formula size falls below the threshold of 2s by 3 is this V. And in this walk, remember that we'll always go to the child where which is heavy. So heavy means subtree is bigger, the size of the sub formula is bigger. Well, if the two are the same, then you can just say you move to the right. Anyways, we could have transformed the formula so that it is right heavy. You can assume that the path always goes to the right, because otherwise you can just flip that part. So all those things you can do efficiently. So this is what we are calling CV, the subtree or the sub formula rooted at V. And so now what we will do is we'll use this frontier node to rewrite the final polynomial being computed. And yeah, let us first make this simple observation. So the size of CV is obviously less than or equal to 2s by 3, and it is at least, correct, it is at least s by 3. The reason is its parent has size more than 2s by 3 and CV is heavier, it's at least s by 3. In fact, you can even take it to be strictly. And let us use the old notation of CV equal to y. Right, so that's the modified circuit after removing this V, replacing it by a new variable y. So the original circuit C can be written as A times CV plus B. This is obvious because if the parent of V is a multiplication gate, then no, that is not clear. This is not about degree.
I think it's obvious because it's a formula. So if you have CV square, that means you have seen that vertex twice.
Yes, so it is obvious by the fan out of CV. The fan out is 1, so it contributes, so it gets multiplied by some A if the parent of V was a multiplication gate.
So it might eventually get multiplied.
And eventually it might, yeah, eventually it will get multiplied, sure. So it's just A CV plus B. And what is CV equal to y? So you remove CV, replace it by y. And what do you know about AB? So for polynomials AB that are free of y, right, so that is their speciality. They are y free. Okay. So these two identities basically eliminate AB from this. AB are the unknown polynomials, so you can eliminate them and you can write C as just a simple formula in CV and CV equal to Y. So let us do that. So yeah, maybe in steps. So what is B? B is equal to CV equal to Y with Y 0. And what is A? So A is CV equal to Y at Y equal to 1 minus B. So that's it. Right, you have A and B, and so you have rewritten C in terms of these, in terms of CV and CV equal to Y. So this is clearly reminiscent of the derivative construction. And this is again a recursive proof. So instead of using the way C was given before, you use this representation. Okay, so this representation is basically C. To compute C, you have to compute CV equal to Y recursively, and then take two different evaluations, difference of that. So an addition gate, and multiply it with CV, which is again a recursive call, and then add B, which is again a recursive call. Right. So let us analyze this new representation. This can be done efficiently if you want an algorithm, but it is also enough to see this as an existential proof. So that's the new representation. Okay, so we'll write C in this way, and note that C of V equal to Y this plus CV is smaller than the total size S, right? So which means that CV equal to Y size is less than equal to, so CV was was greater than S by 3, right? So this is so that is the key thing, that when you are making this recursive call, CV equal to Y is smaller by a fraction. Okay, so recursive call is happening on this small an instance, and CV as well, right? Yeah, so this should now be taken as the motivation for whatever we are doing in this proof. So we have identified a frontier gate such that when we do recursive calls, two recursive calls, both of them are fractionally smaller. So this reminds you of merge sort, right? So you know that something good is going to happen in this recursion. So equation 1 involves 4 formulas of size two S by 3. So thus we get the recurrence for the size function, let me say. Thus we get the recurrence and similarly for depth you will get a recurrence. So if you started with a formula of size s, then this process will give you ultimately a formula of size bracket s, which will be smaller than 4 times if you had started with 2s by 3 plus some constant overhead. This is, so remember that this is the final formula based on 1. So you start with formula size s and you end up with formula size of s. Okay, s is being thought of as a parameter, and this recursive proof will give you this recurrence. And what is the solution? So size of s is polynomial in S is, yeah, sure, certainly subcubic, not even cube. So it is between quadratic and cubic.
S to the power log 3 by 2.
Correct. Yeah. And as an exercise, you can show that the depth function for the formula, which is actually the important thing, we wanted to show depth. So the depth of this resulting formula based on equation 1, repeated applications of equation 1, this will be the number of recursive calls, right, which is log of s. Is that clear? So this is just the number of recursive calls. Yeah, so we have a super quadratic size log s depth formula, which is equivalent to a given and arbitrary formula of sizes. Right, so this is a very powerful theorem. Any questions? So what is the problem if C was a circuit and not a formula?
Multiple now, so why do you
The formula will, the equations will be wrong.
Ey plus b will be a polynomial in y, but y degree.
Correct, yes, yeah, so, right, A and B will not be y free. And then what happens? So since A and B are not, I mean in the case of a circuit, or if A and B were not y free, so that we have used implicitly here. So if this B is a function of y, then this equation is not computing B at all, it is computing B 0. Right.
We write like CBY equal to some polynomial in y and
Sure, you can.
extract the y free thing, so summation AI by to the I.
Right.
And the AI and then
Correct, but then it's not the 4, it's not a constant. The recursion is now full-fledged.
The degree of y can be pretty high, right?
It is D. So the recursion is now into D instances. So this is full-fledged. So you will get super poly here. Yeah. So that was an implicit understanding we had, that these two equations are indeed giving you A and B, because A and B are not functions of y. If they are functions of y, then obviously you are not computing B, you are computing B of 0, right? That's the problem. So this proof has to be drastically changed, but at least now you can make the conjecture, you can ask the question, why is this not true for circuits? right? Circuits also should have a log depth. After all, they are a much stronger model.
So then you can probably count and say that there's a lot of circuits.
Uh-huh.
So, I mean, there's more circuits than formulas, but
No, but for
say that.
no. But counting argument is only on the size. How will counting tell you specifics about depth and fan in and fan out?
Okay, yeah. So final and final.
Yeah, these are semantic details in your inside your model. You cannot see this in the count. Counting is just for the number of representations. You are just thinking of your circuit as a string, and then you just see the size of the circuit. Everything else is invisible. Yeah, so that's the problem. Yeah, I don't think we can do it now. So let's just mention it here. In circuit C, CV equal to Y and CV overlap, and the proof fails. So we'll try to run the same proof based on the degree. And recursively reduce it. Yeah, so we will, instead of defining the frontier with respect to size, we will define it with respect to degree. That is just one thing. There will be more details which we will see when we come to it, and that will give a similar depth reduction for circuits as well. But in that case, there will also be more parameters. So here there was only one parameter, which is S. In the case of circuit, if you just work with the size S, then the degree can be as high as 2 raised to S. Right, so log of 2 raised to S is again S. So this is not impressive at all. So what you would want to prove is that if your polynomial ultimately has degree D, then the depth required is log D. Okay, so already the semantic suggests that you should use degree as your potential function. Okay, and we'll do that. So we'll define frontiers with respect to degree and then show that in the recursive calls, number is only log of the degree.
In that case, then degree is bounded by S.
No. Well, degree is D. There are two parameters. Circuits have two parameters.
Everything poly, right? Not to worry.
No, but what he is saying cannot be achieved. If you are given size as circuit, degree S may not give you anything, because the circuit may be computing something much more than S, like 2 raised to S, by repeated squaring, for example. So D is a different parameter. Whatever D is, based on that you get depth.
Useful in case of leaking.
Yeah, exactly. It is useful in those cases when D is poly in S.
Also we could have done with degree, right? What is the problem with
Well, we have to see. We have to then make these statements that degree of both the things are small. So we can check that. But okay, any other questions? Okay.